Hello and welcome to another Physical Sciences 3 lecture. We're starting Criterion 7 today, which is about chemical structures and properties. And in the first part of the course, we're going to look at bonding and precipitation, and organic chemistry comes later on. Okay, so this will be familiar to us all from Criterion 4. So chemical properties due to the structure of atoms. So looking at this atom, this is the outer electron shell, this first one here, this first arrow. So we can call that the valence electrons are in the outer shell. Okay. And in here we have the nucleus, of course, and that has a positive charge, positively charged, due to the protons in there. The nucleus is positively charged. It's looking a bit funny. Okay. And the periodic tables, we covered that in Criterion 4, so please go back and review that. I don't want to spend too much time going over that one. I guess the things you need to remember specifically are the Roman numerals. So groups 1, 2, 3, 4, 5, 6, 7, and 8 in Roman numerals, and they have the same number. They have the same number of valence electrons in those groups. So it's going down the periodic table. That's going to be very important in chemical reactions. So if you're not sure with your Roman numerals, then please go over that again. Chemical reactivities in groups. So in groups 1 to 4, so just remember that's a 1 and that's a 4. The chemical reactivity of the elements increases down the group. So, example, lithium is less reactive than potassium, and we actually saw that in a reaction in our class, in one of our sessions. Group 1 to 4 elements need to lose electrons in order to gain a stable outer electron shell, so they need to lose them. As we go down the group, the outer electrons are further away from the nucleus, therefore the electrostatic force between the nucleus and the valence electrons are lower and hence more easily lost. Okay. And in groups 5 to 7, the chemical reactivity of the elements decreases down the group. So, for example, bromine is less reactive than chlorine. And in group 5 to group 7, atoms need to gain electrons to attain a stable outer electron shell. The shorter the distance to the nucleus, the greater electrostatic attractive force to attract the additional electrons. So these reactivities is all about the electrostatic forces that are going on. And we'll look at them more when we talk about bonding and things. So we're going to talk about bonding in this course. We look at metallic bonding, ionic bonding, and covalent bonding. And in covalent bonding, there is covalent molecular and covalent network. So we'll look at all of those in much more detail. The first one in this video is concentrating on metallic bonding. So metallic bonding is where atoms are bonded by the electrical attractive forces existing between positive metal ions held in a rigid lattice and delocalized mobile negatively charged electrons. Okay, so that's a bit of a mouthful. Let's have a look. We'll skip a bit and we'll have a look at the model for them. So what that's basically saying is you have these essentially nucleus in here and they're all positively charged in here. So all these big circles have got positively charged, and then they're surrounded by negatively charged a sea of mobile electrons. So around this yellowy bit, there are electrons all going through there. So they are all electrons, and this sea of electrons allows metals to have some unique properties. So if we go back up, and this is a table of characteristic properties of most metals. So most metals have a luster, so it means they're shiny. And non-metals are not lustrous, which means they're dull. Okay, or not shiny, basically. That's what luster means. That's because, like the sea of electrons, they allow for the reflection of light, which makes them shiny. Metals are solid at room temperature. Some metals are solid, some are liquid, and some are gaseous. But most metals are solids at room temperature, except for mercury. Mercury is an exception. I might just put that in here. Mercury is exception, and that's a liquid at room temperature. But most metals are solids at room temperature. Metals have a high density. Density is how much mass per volume. Okay, so kilograms per meters cubed, that's density. Metals are good conductors of heat. We'll speak about that a bit more. They are also good conductors of electricity because of the sea of electrons. Okay, so the electrons are able to move throughout the lattice, carrying charge. That's a key concept that we'll keep on coming back to. Metals have high strength. Metals are malleable, can be beaten into shape, and ductile, can be strawn or stretched into wire. Metallic oxides are basic. Ions of metal have a positive charge. Okay, so we will talk about that a bit more. Basically, when something's basic, it accepts positive charge, H plus ions, and when they are acidic, they donate. So donate H plus ions. So we'll talk about that a lot more when we talk about acids and bases, and that's this one model. Ions of metals have a positive charge because they lose electrons. And ions of nonmetals have a negative charge because they gain electrons. So this is some things in here. We have some other ones about nonmetals. Some interesting words. So brittle means that they will easily broken. Fragile, I guess, is another word. And they snap. They can snap when they're broken. They'll snap. Just some other things. Non-metals have low density, so just the opposite of metals. Non-metals are thermal insulators, so they do not conduct heat. Non-metals are electrical insulators. They do not conduct electricity, so do not conduct electricity. That's what an insulator is. And just similarly, if they're thermal insulators, they do not conduct heat. So just the opposite of metals. Okay, so that's some ways we can, if we're not sure if something's metallic or non-metallic, we can often use those properties to determine whether they are a metal or a non-metal. And we're coming back down to our model for metallic bonding. And we've kind of spoken about that a bit as well. We'll just quickly go through it. Positively charged ions are arranged in a rectangular three-dimensional lattice, like these ones. So these ones are all positive and they're in 3 dimensions. So all in all different ways. So 3 dimensions. Okay. To form the ions, each metal atom sets free one or more electrons. These free electrons do not belong to any particular atom and are said to be delocalized. Okay, so they can be shared amongst many. That's what delocalized means. Shared amongst many atoms. The sea of delocalized electrons can move throughout the lattice. Okay. So the attractive forces between the positive metal ions in their fixed positions and the delocalized electrons are metallic bonds and hold the metal atom together. So it's so they're electric forces. Metallic bonding extends throughout the lattice, and thus the metal lattice is described as a continuous lattice. So lattice is like another word for structure. Lattice is structure. Because the delocalized electrons are moving randomly throughout the fixed ions, metallic bonds are non-directional. Rightio. So here is some of those properties in more detail. So if you need to explain these when you're asked questions, then you can refer back to these notes. So electrical conductivity. Metals are good conductors of electricity. So electricity is a flow of electrical charge, as we saw in our physics units, because they contain mobile charged particles. That is, the mobile delocalized electrons within the lattice. When a potential difference, so remember that's voltage, is applied across a piece of metal, electrons flow into one end and the same number of electrons flow out the other end. Okay, this is the general movement of electrons along the metal, so electricity is charged particles. Densities, okay, so they say that the metal ions are tightly packed in the metallic lattice, so there's a lot of stuff in a small volume. Metal melting points and boiling points. The metal points and metal, I think that's meant to be melting. melting points and boiling points of most metals. That's not right. The melting points and boiling points of most metals are high because a large amount of thermal energy is required to overcome the strong electrical forces between the positive ions and delocalized electrons. So this is an important concept because it'll come back for all our other types of bonding as well. If something has a high melting point or boiling point, then it means it needs a lot of energy to break the bonds, a lot of thermal energy or heat energy to break the bonds. If it has a low melting point or boiling point, it doesn't require much, so it doesn't require much energy to break the bond, so there's not much, so the bonds are not strong. And we'll talk about them more when we talk about non-metals as well. These are some new words as well. Malleable means, I like to think of it as bendy, but basically you can put it into shape, and ductile means is stretchy. So ductile is stretchy. You can stretch it thin into wire. So stretch to wire. And bendy means you can be bent into shape. Okay, so we can take on many shapes. Bendy, stretchy. Okay. So it's because of these sea of the localized electrons, basically allows movement, and the electrostatic forces are still present. So it means that the forces holding the structure together are still in place, even if you distort them. Conduction of heat. Metals are good conductors of heat because the delocalized electrons again transmit the energy vibration of one positive ion to its neighbors. So again, delocalized electrons allow for heat to conduct. Okay, and luster. The presence of free electrons, again, the delocalized electrons, free electrons, causes most metals to be excellent reflectors of light, of visible light, and are shiny. Excellent. All right, so we've got an example. Good. Example, in terms of the metallic bonding model, why is copper a good conductor of electricity? Well, all we need to say is that when a potential difference is applied, just remember that is voltage to a piece of copper. Copper, delocalized electrons. Delocalized electrons are free to move towards the positive end. Carrying electric charge. Okay, so, and then that is a flow of current, and that says current. So current is just the flow of electrons. Okay, so that's why they're good conductors, because of the free electrons. We've got some alloys here. So not all metals are made of just one element. In fact, the vast majority of metallic solids that we encounter in our lives are a mixture of several metals. These mixtures are called alloys. You've probably heard of alloys before. And they're just a mixture of metal, and you might be like, well, why do you want to mix metals? And it's because alloys will have properties of all the metals that make them. That are in them or that make them. And a good example here is we've got steel and stainless steel. And what you might notice when you look at stainless steel is it is shiny, so lustrous. Oops. Gee, that's not very good. It's not very well written. So this one is lustrous or shiny. Writing too quickly. And this one is dull. Steel is generally dull. So what you could say is that because of the chromium and nickel, those properties are shiny. So stainless steel is more shiny than regular steel. So